everybody. Welcome to today's COSI seminar. This is the last seminar of the semester. Professor Allan Franklin from the Department of Physics here at the University of Colorado. Professor Franklin began his career as an experimental particle physicist. He received his PhD from Cornell University. For the last 35 years, he has been working as a different on the history and philosophy of science, particularly on the role of the experiment in physics. He was twice chair of the Forum on the History of Physics of the American Physical Society and a member of the governing board of the Philosophy of Science Association. And he serves in many editorial boards and now switched for the last 35 years to the history of physics and experiments. So thank you for coming.
Thank you, Ariel. Let me just preface these comments by saying, one, I apologize in advance for not including any experiments from optics. I am a strong believer in the view that you ought to know the science well if you're going to do the history and philosophy of it. And so I restrict myself to those aspects of physics I know reasonably well, which is high energy physics. And even then, I talk about older stuff. So this project began with some discussions with my good friend and erstwhile deadly enemy, Harry Collins. Harry and I have been at each other's throats, not literally, but figuratively, for a long time now. But we have recently found an area of interest for both of us in which our differences don't matter and in which our various expertise merge nicely. Harry is, by the way, the foremost chronicler of gravity wave experiments. His books, Gravity's Shadow and Gravity's Ghost, are really the best stuff that's been written on the history of gravity wave experiments. Not that everything in them is right, but it's really first-rate stuff. So he asked me a question about changes in what one requires as statistical significance for making a discovery claim in high-energy physics. This is a real issue in gravity waves. In fact, the discussions are quite explicit. They said, we don't want the high-energy people making fun of us because our results aren't statistically significant enough. So I decided to look at the history of high-energy physics in the light of these questions. And what I found is if you start in the 1960s, there is no standard for discovery. You find the results reported as low as 1.5 standard deviations, which is hardly a big effect. In fact, in the 60s, you find a claim that charge conjugation invariance, a major symmetry principle, was violated on the basis of a 2.7 standard deviation or 2.7 sigma effect. But in the 60s, there was no criterion. Technology demands. This is a claim of a discovery of a new elementary particle. It's not, by the way, this peak. This peak was already known. This is the omega. It's this peak down here. This is by Ehud Pevsner and company. It's the discovery of the eta zero meson. And it's actually 36 events total above a background of 12, and the background is in fact overestimated. So it's actually a bigger effect, but they don't make any claim about standard deviations or anything. By the early 1970, the criterion was 3 sigma. If you didn't have a 3 standard deviation effect, you couldn't claim you had seen anything of significance. Now, the probability of seeing a 3 sigma effect in a single bin is 0.27%. Now, in the early 1970s, the criterion actually changed. You can document it. The story that received wide circulation in the high energy community was that this was due to Art Rosenfeld at Berkeley, who was a member of the particle data group. They're the group that combines all the data on high energy physics and tells you what the values are. And what Rosenfeld did was he pointed out that given how many graphs high energy physicists plot a year, you were going to see a lot of 3 sigma effects, even if there was nothing real there. That it was just likely that, and I did the calculation, the chances of seeing a 3 sigma effect in a 1,000 bin graph is 93%. So in the early 70s, it changes to 4 sigma. The probability of 4 sigma in 1 bin is 0.0064%, and in a 1,000 bin graph, it goes down to 6%. Now, and again, this was an informal criterion. My colleague Tricia Rankin was in the early 80s looking for dibaryons and was told that if she didn't see at least 4 sigma, she couldn't publish. This was from her advisor. In the mid-90s, you see the beginning of a change. In 1994, the CDF group at Fermilab, the collider detector at Fermilab, publishes 2 papers, both of which are entitled Evidence for Top Quark Production. In 1995, they publish a paper, Observation of Top Quark Production. Now, what had changed? In 94, they had a 2.8 sigma effect above background. In 95, they had 4.8 sigma. This is the beginning of what has now become a rigid criterion in high energy physics. It's enforced by both the editors of journals, physical review letters, physical review, physics letters, and I can document this. And it's enforced by the groups themselves, Babar, CDF, D0, CMS, and Atlas, the 2 big groups now at the Large Hadron Collider, that if you don't have 5 sigma, it's why, for example, nobody is claiming that they've seen the Higgs boson. The effect is, at best, 3 sigma right now. Of course, the opera result was more than 5 sigma, but that's up for grabs now. That's the faster than light neutrinos. Okay. Now, if you want to say observation of, and that means discovery of, you have to have at least 5 sigma. Anything less is evidence for, measurement of. And I've even looked at hybrid papers which have both observation of and evidence for in the title. And if you look after 2006, you see no violations of the rule. all the observation of are greater than 5 sigma, all the evidence for are less than 5 sigma. It is actually a rigid rule, which is interesting. Now, it is not at all trivial. It's not just calculating the sigmas. It's not just a numerical calculation. It depends on knowledge and judgment. In fact, there are arguments as to how you should calculate the number of standard deviations. Should it be the signal divided by the square root of the background? Or should it be the signal divided by the square root of signal plus background? And some people even say it should be the signal divided by the square root of the signal plus twice the background. And those give very, very different answers. I can show you papers where it goes from above 5 sigma to well below 5 sigma. And this is given by the groups even. So, and also it depends crucially on calculating the background. That's not at all a straightforward process. In fact, it's a very important process, as Peter Gallison has pointed out, but it does demand real knowledge and real judgment on how to calculate. And I'll give you an example of where people didn't do it right later. Okay, now, to show you how it's enforced on the archive where all high energy physics results are posted well before they're in print, CDF and D0, the two big groups at Fermilab, published results on single top quark production within 2 hours of one another. Both of them, interestingly, were 5.0 sigma. Now, one speculates that there was an agreement not to publish. They would publish at the same time, and that D0 jumped the gun to get their 5 sigma out first. This was confirmed for me by a member of CDF, so it's slightly questionable. But, okay. So this whole history suggested to me that it might be worthwhile to look at other changes in the reporting of experimental results in the period from 1893 onward. Now, why 1893? Does anybody know why I chose 1893? It's actually not arbitrary. What? No, that's 1881. Michelson-Morley is 1887. Michelson is 1881, no. 1893 is volume 1 of PhysBrev, Physical Review. And I'm going to concentrate mostly on papers in Physical Review. So essentially, I covered the 20th century. And I'll almost exclusively talk about Physical Review and also about elementary particle physics. And some of the issues I'm going to discuss are experimental details, exclusion of data, the possibility of experimental bias, selectivity of data, how much history people give, the scale of the experiments, and a realistic versus a schematic presentation of the experiment itself. So these are the issues I will talk about. Now, exclusion of data is what we refer to as talking about bad data. That's data when you are not convinced that the apparatus is working properly. And one of the first examples comes in 1894. Is from a paper by Kennelly and Fessenden on the coefficient of temperature dependence of electrical resistivity in copper. They threw out their first 4 runs, and they tell you explicitly, because in the first 4 runs, they got differences in the resistivity of copper depending on whether they were heating it or cooling it. And that was something they did not expect to have if their apparatus was working properly. It should be a function only of temperature, not on how you get the temperature. And they're very explicit. Arthur Compton, in the famous experiment in 1923, has 3 different runs. He throws out run 1 because there are too many background electrons in his cloud chamber photographs. Okay, selectivity, however, is applied to good data, where the apparatus is working properly. And it's applied to reduce or eliminate backgrounds that might mask or mimic the signal you want to see. And it is central to certainly high energy physics and other areas of physics. Now, there's an interesting form of selectivity that's going on now at the Large Hadron Collider. My friend Corey Caracca and others are working on this. At the moment, the event rate at the Large Hadron Collider is 800 megacycles. 800 million events a second. You can only record of the order of 100 or 200 events a second. That's with a computer farm of 1,000 PCs. And these are not the ones I have. These are better. So you need to reduce just the data acquisition by a factor of 1,000,000 to make it. And how you do that and how you justify it is a very interesting and important question, and it is being discussed at great length among both the physicists and the philosophers. There's a lovely project at Wuppertal in Germany, which is a collaboration between the Philosophy of Science group and the Atlas group at Wuppertal. Now, Robert Millikan engages in both in his famous experiment to measure the charge of the electron. Millikan talks about and this is his 1911 paper, he says they're omitted not because it would change the final value of E, it's not affected, but because the experimental uncertainties are large. He's talking about excluding very fast or very slow drops. The fast ones, you have a problem with timing. The slow ones, you have convection currents and residual Brownian motion. And so he says it's unreliable, so it's scarcely legitimate to include it. So Millikan has, I think this is legitimate. His apparatus isn't working as well as it might. However, he says in his 1913 paper, it is to be remarked that this is not a selected group of drops, but represents all of the drops experimented upon during 60 days in which the apparatus was taken down several times and set up anew. That's a lie, flat out. Millikan took data for 6 months. There were 175 drops in his notebooks. I know, I counted them. And most of it, by the way, is legitimate. He wasn't sure the apparatus was working. But here's, and it's hard to see this one, this is a data sheet from April 16th, 1912. It's toward the end of his experiment. At this point, the apparatus is working really well. This is probably the most consistent event that Millikan had in terms of the numbers you get. And it's beautiful, except you get 0.6 E. Down at the bottom, Millikan says here, won't work. And he never publishes it. Why didn't he? He was involved in a controversy with Ehrenhoft over the question of whether charge was quantized, and he thought this would give Ehrenhoft ammunition, which it probably would have. So Millikan did not publish it, failing to recognize that intrepid historians of science would track it down. These days, nobody has, almost doesn't have notebook. Everything gets recorded on computers, so you can just clear the hard drive. Okay, and to show you how selectivity works, here's an experiment that I actually worked on back in the old days. This is an experiment to measure the K plus E2 branching ratio. It's about a part in 10 to the 5th. You have a beam coming in, it stops. The electrons go out here. You measure the momentum in a magnetic field. You say if it's an electron, because this is a Cherenkov counter, you have a range chamber. Okay? And here's what we get. Well, oops. Notice this is where we expect the K plus E2 events, and a rough calculation indicated we would get of the order of 10 events. If they're there, they are extraordinarily well hidden in this huge peak. And so how do we deal with it? We engage in selectivity. The big background is muons from K mu 2 to K, which have a different range. And so we applied a range cut, and you'll notice we get rid of almost everything. Still too many. The K plus E2s would be here. We then applied a decay track matching criterion because the muons decay, and we are doing better. Down here we're getting, the region is 242 to 252 for the K plus E2s, and then we do sample events with range less than 45, track matching and time criteria, and we end up with 7 events in this region. In an interesting thing, which I can tell you since I wrote the paper for the group, in those days we had them typed by somebody else, and it said after this calculation, we obtain a total of 6 events. That includes background subtractions. The typist typed it as after miscalculation, we obtain a total of 6 events. She might have been more astute than we were. Okay? Now, one of the problems one also faces here is the problem of, in this case, we didn't know the effect on the final result until we did all the cuts. One of the problems you have is, suppose you know the effect of on the final result when you make the cuts. This introduces the possibility of experimental bias, tuning the cuts to get the result you want. This has, in fact, explicitly happened. If you look at the results in the 80s and 90s from the GSI at Darmstadt on low mass E plus E minus, the effect they see is strictly a result of selectively applying cuts, including some that you can't imagine why they did it, except to generate a signal. And so, and there are techniques for avoiding it. This is known as blind analysis. You set the cuts without knowing the effect on the final result. And there are different techniques. The hidden signal box method, where you hide the signal area and set the cuts elsewhere. Or you can do what was suggested when William Fairbanks Sr. claimed to have observed fractional charges, quarks, free quarks, on superconducting niobium spheres, Luis Alvarez suggested, hey, you know what the value is when you select your good data. Let me add a random number. And so then you select the good data. Alvarez did it and the effect went away. So, example. Now, if we look also at the history, how much history gets presented, in the early days, it's much more extensive. They felt obligated to give you. And it had two reasons. One was motivation. If there was a disagreement in the values, that was a reason for doing the experiment. There was also an epistemological reason that if you got a result which agreed with previous results, it gave more credence. That raises the other problem of the so-called bandwagon effect, getting a result. Again, blind analysis will work against that. Now, in contemporary papers, you get almost no history. Now, Kennelly and Fessenden, in their experiment on heat coefficient of resistivity, oh, this is just a set of cuts for Babar. They say they're talking about somebody else's results which disagree by a lot. And they say, aside from this remarkable and perhaps debatable statement, the graph is a straight line. So they question the absolute value, but they note that they get a straight line, which is what you expect. Now, my favorite paper out of this one is a paper by Edwin Hall. Edwin Hall is a famous physicist known for the discovery of the Hall effect, which is a big deal in condensed matter physics. Would you say that? The fractional quantum Hall effect. Hall did this while he was a grad student. It was his dissertation, I think. By this time, he's a professor at Harvard, and he's doing an experiment on, do falling bodies move south? Now, everybody knows that falling bodies move east because of the rotation of the Earth. But back in the 17th century, Robert Hooke suggested a theory that said that it would not only move east, but also move south. Now, Hall proposed to investigate this. He actually writes two papers. One is totally devoted to the history. One is his experiment. And as he says, it's not the most important problem. This is 1903. It's not the most important problem in physics, he says, but it has the dignity of age and the charm of mystery. And it starts in the 17th century with Hooke versus Newton. And this is Hall's comment. Moreover, Hooke, a brilliant genius, but a somewhat uncertain character, had committed himself in the most open way to the opinion that experiment would reveal a southerly deviation. In a man of his reputation, such a bias is not to be overlooked. And yet it is hard to believe he deliberately lied to his associates in the Royal Society. And he says Hooke's evidence is not to be altogether. I can't imagine anybody writing this in a contemporary paper. Later there are a series of experiments, but later, and they all, by the way, tend to give positive results. Later, Benzenberg does an experiment in Vienna in a church tower, dropping objects, and he first gets a positive result. And Hall says, was Benzenberg, in undertaking this research, prepossessed in favor of a southerly deviation, possibly for he knew of the work of Hooke and of Guglielmini, and he had not yet received from Gauss those letters which finally convinced him of the improbability. Benzenberg does the experiment in 1802, and he gets a positive result. He then gets a letter from Gauss telling him that Gauss and Laplace had calculated and there's no effect. 1804, Benzenberg gets no effect. He says, the honesty of Benzenberg is not to be questioned, but we may well ask how far he may have been influenced in selecting his evidence from the whole body of data by the knowledge that the authority of Gauss and of Laplace was dead against. Experiment a bias, this time by theory, by theorists. So one can't imagine when recently CDF and D0 got different results on the similar phenomenon that they would say the honesty of CDF is not to be questioned, but we may wonder. Okay, in 1943, Schull does an experiment on electron polarization, double scattering of electrons, and he discusses only 3 experiments and misses out on a fascinating history which involves fraud, experimental problems, and finally, and failed theoretical attempts. This casts doubt, by the way, on Dirac's theory of the electron, because the calculus, and he just doesn't talk about it, which is just as well, since I devoted a whole chapter of a book to the non-discovery of parity non-conservation. But yeah, there were all sorts of fraud involved. Here's Hall's events, summary of the results. Hall gets essentially no north-south. He does get an east-west, which is what you expect. It's off by a little, but within experimental uncertainty. Okay. Now, here's the total history as presented in an experiment by the Babar collaboration. That's 600 high-energy physicists. These branching fractions and charge asymmetry represent an improvement over previous results. That's it. That's the history. And if you want to see what those results are, you have to look them up yourself. They don't care. Okay? Now, another thing that happens is what you get in the 20th century is an increasing abstraction on presenting an experiment. It's a change from what you might call a realistic view of the experiment to a more schematized. Duhem, in the late 19th century, philosopher, talked about the distinction between the ideal experiment and the real experiment. And for Duhem, it occurred in the mind of the experimenter. But we see in the 20th century is this increasingly appears in the literature. As we will see, the experimental apparatus disappears almost in high energy physics. Okay, here's from Kennelly and Fessenden. And they tell you, here's the cylindrical glass bulb, 15 centimeters long, 3.1 centimeters, 2. And they tell you why they did it. They give you the details so that if anybody wants to reproduce them, they could do it. Now, let's face it, The only people who could reproduce CMS now is Atlas. Experiments are becoming much more complex, much more expensive. Replication is not easy. Here's Hall telling you not only that what details of experiment, he tells you who's doing what. He says the routine leveling of the top plate with plumb line hanging from, he did that. The routine was different, was done by the assistant. Nobody would tell you that anymore. Here is Millikan's apparatus. I don't know if I told you it was his apparatus for the photoelectric effect, you'd probably believe me. This is the one for measuring the charge of the electron. Here, however, is his diagram. But notice it's pretty realistic. Glass wool here. God, he puts in the battery symbols. And by the way, Millikan remarks on this, that the diagram is more informative than the picture. He says this in his book, The Electron. He gives you a picture of the apparatus as well as a diagram and says, look, if you want to understand what's going on, look at the diagram. Here's an experiment. This is Scholl's experiment. It's, as you can see, 1940s. Very realistic. If anybody can tell, I know this experiment. I've studied it. If you can tell what the hell's going on in it, you're better than I am. It's not trivial. Even if you could read the captions. Now he tells you what's going on in a diagram. This is double scattering. This is a transmission experiment. This is backward, this is forward, where the beam goes through the target. This is a reflection experiment. And it turns out this makes a huge difference in the experiment. Nobody realizes this until the work of Scholl and company in the 40s. Here's the K plus E2 experiment. It still has aspects of looking realistic, kind of. But now it gets more and more abstract. This is E791 at Fermilab. Data gets more abstract. Here's, if you consider cloud chamber, this is the decay of a lambda in a cloud chamber. Now, how many of you, in looking at this, identified it immediately as a lambda decay? Showing, in fact, as Norwood Russell Hansen pointed out back in 1958, there is more to seeing than meets the eyeball. I see it, I look at that, and it's a lambda. That's because I've looked at lambda events. Because look, this is a short, dark track. Protons stop faster. The meson goes further. But this is a kind of realistic picture. Here is one of the most famous events of the 20th century. I'll give you a hint. It starts here. Everybody see it? I don't. It's the discovery of the omega minus, the thing that confirms the quark model, the eightfold way. And when you get the diagram, it makes sense. Here's an event from CMS. I don't know, it looks like a bale of hay to me. Here's a lambda reconstructed. Notice how abstract it is. The chambers, the counters are all represented by blocks. And here's the two tracks. Notice you have a short positive track, a long negative track. It's the same lambda. Okay, oops. Okay, so you can see that this increasing abstraction takes on concrete form. Okay, so the project started with sigmas, and I'll end it with sigmas. This is what I refer to as the case of the disappearing sigmas. This is, I don't know how many of you know, this is the case of the infamous pentaquark. This is a 5-quark state that was predicted theoretically, and a large number of early experiments claim to have observed it, and then a large and more credible number of experiments didn't find it, and the pentaquark is gone. But here's the pentaquark. This is, oops. This is the pentaquark at around 1540 GeV over c squared. This is the background. And this is reported as a 5.6 sigma effect. Clearly visible. The curve, by the way, is drawn to help the eye. Okay? This is reported in 2003 by the CLAS collaboration at CBAF. The CBAF Large Acceptance Spectrometer, the nested acronym, CBAF is Continuous Electron Beam Accelerator Facility. And they get 5.2 plus or minus 0.6 sigma, and they claimed observation of the pentaquark. In 2006, they publish another paper, Search for the Pentaquark. Now, everybody knows what search for means. What does it mean? My first publication in high energy physics was search for photoproduced eta-0 meson. We didn't find it, right. It was published in a journal my advisor called The Garbage Can of Physics, which I think was unfair to Il Nuovo Tremendo. In 2006, the class collaboration gets 6 times as much data, and they see nothing at 1540, 1550. It's just a beautifully smooth curve. And what they do here, this is 6 times more data. They don't combine the data sets. They use this to get a better estimate of the background and claim the result has been reduced to 3.1 sigma. It's an odd way of dealing with the data. You're essentially throwing out all the statistical power of the later result. Now, they didn't repudiate the previous result. Now, in 2008, now let me make clear that in 2006, the class collaboration published 3 other papers giving high statistics results against the pentaquark. In 2008, they do a Bayesian analysis. We were discussing this earlier. This is a Bayesian analysis, this is the gospel according to the Reverend Bayes, that the probability of a model given the data is the probability of the data given the model times the prior probability of the model over the probability of the data. This is Bayes' theorem. And what they calculate is a ratio. The probability that there's a peak given the data over the probability that there is no peak given the data is the probability of D given MP, etc., where MP is a model that includes a peak and M0 does not. And they assume that the model with the peak is equally probable to the model without a peak. I mean, there are two choices. They might be equally probable. And so they calculate the log of this ratio. And what they find is that the log of that ratio for their original data set is minus 0.408, which tells you that the probability of the data of the model minus the probability of data given the model with no peak is 0.66. The later, that says it says indicates weak evidence in favor of the data model without a peak in the spectrum. What this means is that while they still don't give up. What this means is that while a data model including a peak gives a better fit by eye, it does not compensate for having to introduce, since the evidence does not conclusively rule out a peak, it is simply inconclusive. Now, my view is that this is fudging. The probability in 2008 that there was a pentaquark is hugely reduced compared to the idea that there was none. They never fit the data without a peak. They were looking for a peak. I know this because I talked to one of the group leaders of this group, actually, and he said he doesn't know why they never fitted it to without a peak. But this is a clear bias analyzing the data to finding what you're looking for. And then the question comes up is, should there be a different standard of evidence for a confirmation or for a new result? This is raised by George Trilling in the Review of Particle Properties. He argues for keeping them the same. I did a brief survey of the high energy group in our department, and the answer that you get is it depends. Depends on how good the previous results are. Now, let me point out to you that this is a table compiled by my colleague, Kevin Stenson, that this is the 10 or so experiments that got a positive result. If you believe them, the number of sigmas, the probability that it's a statistical fluctuation is 8 times 10 to the minus 73, that all these results are a statistical fluctuation. And he says it's a 17 to 20 sigma effect. It's the equivalent of flipping coins 207 to 288 times in a row and getting heads. It's the Red Sox winning 39 to 54 World Series. That was before 2004 when they actually won one. 4 to 5 people in the room being killed by lightning in the next month. It was unlikely, but yet it's gone. And so the moral of the story is, as you all already know, statistics is not a substitute for thought. Thank you. Questions?
I have a question. You touched sigmas completely leaves out the possibility of
Well,
systematic error.
yes and no, I think. There are times when you can make estimates of the systematic errors in some cases, in some experiments, but sometimes you can't. I mean, I remember once back in the old days of the fifth force, which was a proposed modification of Newton's law of gravity, which had a certain currency for 4 years and then disappeared. Somebody said, well, given our, shouldn't we increase our uncertainty by a factor of 2 to take into account unknown errors? And I said, well, why 2? I was the resident philosopher at the conference. Why 2? Why not 3? An unknown error is unknown. You don't know how to take it into account. But in some cases, for example, as in, for example, background subtractions using Monte Carlo calculations, you can actually calculate that systematic error. You can put in different parameters and see how it changes. So that's a possibility. There are times when I think you do know the systematic error well enough. You've heard of the Lord Snowden box. One of the great examples. Lord Snowden was the husband of Princess Margaret. They were both the same height. Yet in every photograph of the couple, Lord Snowden was taller. How could this be? It turns out what they did was they either they typically photographed him on steps. And Snowden was on a higher step. This led Private Eye, the British humor magazine, to suggest that there was a box, a Lord Snowden box, that he stood on, and that it came in 3, 6, and 9-inch and could be used for all sorts of purposes. In that case, you would know the systematic error.
So,
But yeah, I think...
it sounds like you're saying that we should not certain groups too strongly when they said there was 5 sigma evidence for faster than light neutrinos. At least in principle, it would have been appropriate to come up with some number.
It turns out that it's not there. It's a systematic error, yeah, but it's a systematic error due to, it seems, at least from what one hears through the rumor mill on the hardware, that there was a loose cable connector. Now, I don't know how that gives you a 60 nanosecond change in the timing, but all I know is, we talked about this earlier, is that the opera leadership has been deposed. That's what we hear, but they are taking new data, and presumably with the connector replaced. But there is a new result. I check with our neutrino experts every so often from Icarus, which is a different neutrino experiment, Carlo Rubia's experiment, which gives results in agreement with the speed of light. Now, there is an earlier result from Minos that's 5.2 plus or minus 2.9 times 10 to the minus 5 above the speed of light. But, you know, that's less than 2 sigma. I wouldn't bet much on a 2 sigma effect. In fact, a 2 sigma effect has a 5% probability. One-sided 2.5. But I wouldn't. But there, I think, actually, I approve of opera publishing. They got, they didn't just rush into print. They did devote a substantial amount of time to checking that result. I mean, if you're going to try to assassinate the king, you better be And you're trying to throw out special relativity, and there's an enormous amount of evidence in favor of it.
That takes us into the question of the appropriate prior to use
Yeah.
in a case like that.
Yeah. I mean, to accept that result means to throw out an awful lot of other experimental work. But then you get this idea, well, could it be that there's a theory that just gives you this small effect for neutrinos? You talk about a couple of parts in 100,000. It would be a very odd theory, but let me tell you, if it did turn out to be correct, I give you odds within 2 weeks there'd be 30 or 40 papers calculating it. It would be on the archive. Yeah.
So you talked a little bit about blind analysis. It seems like in order to be able to do that, you have to understand your experiment really well, including being able to estimate background levels and stuff from various sources. And is that true? And if it is, then what if you don't understand it so well?
Well, if you don't understand so well, then I suggest you not claim more statistical power. But in the case, for example, of the high energy experiments, the hidden signal box, they take a certain area in a plot of two different important variables and calculate the background and extrapolate it into the box from outside. Okay. And that's reasonably reliable. That's one method. The other is the adding the random number method. And both are used, and I think with some success. Okay. And so you kind of trust them. But people, for example, run hundreds of Monte, and this is where you get the power of computers. Let me show you some other things I didn't get to mention. Oops. It's better to turn on the device. This is Millikan's apparatus. It's about a cubic meter. This is CMS, 4,000 cubic meters. But notice, the volume per experimenter is roughly constant. Millikan was himself, or maybe Fletcher, Millikan and Fletcher. CMS has 2,000, so it's still about a cubic meter. The world's record, it's probably been exceeded now, but as of 2009, the world's record for authors on a paper was 2,512. And it may be larger now, because I think it gets very complicated who's an author anymore. This was an interesting one. The second most was on a thing on coronary events with mildly, I think they included all the people who were in the study. And if you look at the number of events, Millikan had 175, K plus E2 had 70,000, Focus had 20 billion, Babar had 467 million, B bar, which was a small fraction of their data. And now, think about it, they're getting events not that they can record them, at 800 megacycles a second. I mean, it was slightly unnerving that my thesis experiment had 12,000 events. At 100 events a second, it would take 2 minutes to get my data. Well, if I told you how we analyzed the data, we had optical spark chambers where you photographed the sparks, Then we projected it onto graph paper. And I recorded the numbers in a notebook, then punched them onto punch cards and ran them through a program on a computer, which we thought was God, which had 32K of memory. I mean, we thought that computer was God. I mean, it made the analysis so much easier. Now, think about it. I have a cheap Toshiba laptop, which is orders of magnitude more powerful than the computer for all of Cornell University when I was a grad student. Yeah?
I have to ask you, what's your current opinion on the evidence for the Higgs boson?
It's a 3 sigma effect, and I subscribe to the fact that 3 sigma is insufficient to make a claim. It's not that I think the 5 sigma criterion, it's an interesting thing where a social agreement has become a rule and it's enforced. My own view is that the evidence is insufficiently conclusive to say it has been discovered.
Do you think we have the equipment right now to increase that to 5 or 6 sigma?
Yeah. I mean, they're hopeful by the end of the year. I get this from my buddies. I still maintain my office is on the one of the high energy physics floors in Gamow Tower, so I can ask what's going on. And yeah, I think it will be determined. Now, whether it's positive or negative, 3 sigma effects have been known to disappear too. 5 sigma effects have been known to disappear. But there, you might worry that it was funny analysis. But yeah, there were effects that that if you believed the statistics, you say, of course it's there, but I, for one, didn't believe the statistics. But on the Higgs, the answer is there's just insufficient evidence. I'm personally rooting against myself. I think it would be more interesting for physics if they don't find the Higgs. You would have to go beyond the standard model. And I think that makes for exciting times. But